this I didn't load on the e-learning, like the last 2 and 3 scripts were not on the e-learning, so sorry about that. I fixed that. You've probably seen that there is actually there already was more complete version of the example we did last time. I mean more complete because there is also the weights of the variances due to the fact that on these polls, some polls had more respondents and some had a smaller number of interviews. So just give me a sec and I show you what I'm talking about. But probably saw it on the e-learning. Okay, that's it. So last time, just to remember what we did, we built a model to construct an indicator of the number of voting or intentional votes for a given party. In Italy, we had a very long time series. It's kind of a daily time series. Actually, we transformed that into a daily time series of actually many time series. We use, I think, just 10, but actually I have 40 of them in this example. And we wanted to build an indicator of the poll of polls percentage of votes for a given party. And we did a simplified version of the version that I actually explained it to you, which is also explained here in this HTML or R Markdown. And actually here there is the implementation for a different party. I think we worked on a Movimento 5 Stelle. Here is the Lega, but all the rest is the same. But here I implemented like a common variance. So actually here there's only one single variance for all the polling institutions, but every single poll has the number of interviews, and so we divide this common variance, which is kind of assuming all the institutions making these polls are equally precise, apart for the sample size they use. And of course, so I include also the sample size here. So basically, this example is very similar to the one we did, which I now loaded on the e-learning. But it's on a different party, and more importantly, I built also a data frame just with for every single institution and for every day with the number of interviews. And so I wrote also the, where is it? The update function. Where is the update function? Sorry about here. So in this update function, if you remember, CFAS needs, in order to fit the model to the data, needs, of course, the state space model, which is this object here. And the parameters we have to put into the model, the unknown parameters, of course, that have to be estimated by maximum likelihood. And in this case, I added one more parameter in this function, and this is the data frame that contains the sample size, okay, of every institution and every poll. So this is the only difference with respect to the example we did on Thursday. So this is the only one variance we have in the state equations. This is the common variance, which is also, see, we just have two parameters. So one parameter is the log variance of the real number of the real percentage of votes, which we are trying to estimate, and which we think it evolves like a random walk. So it's got only this variance. So this is the variance of the random walk. And here we have like, this is the common variance we are assuming, as I told you, that all the polling institutions are equally good in doing their job, and everything just depends on the sample size. So this is the common variance of the error that the institutions make on every poll in estimating the real percentage. And then here I'm just giving to every single so of course this means that the variance covariance matrix of the errors changes every day. Okay, changes every day because every single poll has a different number of interviews. Okay, so this is just a for loop for this loops into the times, you know, the every day. And so we are overwriting over the diagonal of this matrix, which is otherwise equal to 0, with the variance, the common variance, divided by all the sample sizes. Okay. So this is the only difference of this exercise with respect to what we did on Thursday. Okay. And here there are some starting values and so on. And actually the results are similar to what we saw last time. Here I actually also represented also the real percentage computed by every polling institutions. And here we use all the 40 polling institutions as our example just to be quicker. We just use 10 of them. Okay. So this is like a more complete version of what we did last time. As I told you, this is not like a forecasting exercise. As I told you, in general, using this machinery, see? It's in the like the blob of everything. It's R code, data, and that stuff. It's called polls, and then there is the RMD version, so the R Markdown version, and the HTML, which is the compiled version. But it's there, isn't it? No, wait. I think I actually loaded even before the lesson. So, so when I speak about the blob, I refer to this folder here, R Markdown scripts and data from the lessons, and it's called polls. I know it's not there. Oh, sorry, I was convinced it was there. There's just the data. It's just the data. Sorry about that. So I'll load it straight away. Sorry about that. Probably I began that and then I did something else. I didn't close it, and so it remained unfinished here. Okay, now you have it. Okay. Well, anyway, you can go through by yourself. It's not very different from what we did. There's just this more particular update function that has to load also some data about the interviews. Actually, if you have some statistics background, which you have, some of you could have said, okay, but you're using the wrong distribution because you're using Gaussian, you know, we're using linear and Gaussian state space models, but the data cannot be Gaussian because they're just counting of yes and no to the question, are you going to vote for this party? So as I told you, I think I already mentioned that. So the single random variable, if P is the percentage of votes for that party, the real percentage of vote of that party in the population, then the probability that you answer yes is P, okay? But if I sum up many of these answers to come up with the number of interviews where you got a yes, which I obtained by multiplying the percentage times the number of interviews, then this random variable is binomial, okay? So actually binomial would be the right distribution to use in this situation. Why I'm telling you that? Because in the binomial distribution, the variance depends on the mean. What does it mean? Well, also in the Bernoulli, of course, the binomial is just the sum of Bernoulli random variables, right? So if I sum, Bernoulli is the 0, 1 with probability P. If I sum up M, let's say, Bernoulli random variable, I get the binomial random variable, and the probability of a positive number is, of course, M times P. So the number of interviews times the the real percentage of positive answer in the population. And the variance just depends also on the same P. It's just N times P times 1 minus P, okay? So actually, we're estimating the variance, but we already know the variance, and the problem is that the variance depends on the mean, but here the means change over time. So in some way, we're making some approximations here. This just to make things clear. So, because some of you should have told me, well, but you're using a variance which is constant over time, but that's not correct. And I mean, in a Bernoulli random variable, we have like the probability P on having a positive answer, of course, a probability 1 minus P of having a negative answer. So if, let's say, if X is Bernoulli, with P probability, then the expectation, so the mean of X is P, and the variance of X is P times 1 minus P, okay? So you see the mean and the variance, they just depend on the same quantity P, okay? And of course, we could work with the, since we are observing if N IT is the number of interviews at time T recorded by the institution I, then this is just, so this is not, I'm not talking about the percentage, but the number of answer will be a binomial random variable. And this binomial, we can call it Y. So it's a binomial with probability P and number of observation and IT. Again, also in this case, we know that the expectation of Y is just NIT times P, and the variance of Y would be NIT times P times 1 minus P, right? So the P is our real percentage, so the quantity we are trying to estimate, and that changes over time, especially for Lega and for Movimento 5 Stelle. We saw that they move from I don't know, like 20 more percent or 30% to 8% and so on. So this should be changing also, the variance should be changing. So that's the approximation we are doing, okay? So the question is, could I use those models also in state space form? Yes, there are also non-Gaussian, of course, state space forms. We will not see them in this course, but just to mention that actually we could do this right, okay, using the right distribution. In some way, you can think of this. I just mentioned this, and then this will be the last say in this course about not Gaussian state space form, but you may think of the probability of the ith institution at time t, actually not the probability, the number, let's say the number of votes for party, I don't know, for party pi, let's go pi the party, okay. Is distributed as a binomial. We just said it. Of course, it depends on the population percentage of votes for that party, which we call P, which it's changing over time. Okay. And of course, it depends also on the number of interviews. Okay. And this would be our observation equation, which in the non-Gaussian case, okay? And PT, in some way, we have to let evolve as a random walk. Of course, PT is a probability, so it's positive, for example. Actually, it should be between 0 and 1. And so sometimes we need to rewrite this thing in order to compress this random variable to be between 0 and 1. So usually we create our usual random walk, but then we say that PT is a transformation of this variable. Usually we take the so-called inverse logic transformation. So we say that mu t is equal to, well, you can see it this way. You can see PT as being equal to a sigmoid function. So this function of mu t. Okay. Usually the sigmoid we use is this so-called inverse logic function. So it would be 1 over 1 minus x minus. So this could be the function we use. But any sigmoid function would do. So this is just to tell you we're doing linear Gaussian state space model. They're very simple to work with. The Kalman filter and smoother, they're in closed form. They're very simple to apply in computers. Don't think that state space model and with the linear Gaussian models, we can also have such models. And for example, if you're interested in that, CFAS, so the package we are using, is able to manage such a model by using something which is called reweighted sampling or importance sampling, you can call it. Just to tell you that we can go further. And in this way, we could even build the right model if the theory were correct about poles, okay? As I told you, the theory is not completely correct because institutions do apply some corrections. Institutions tend to speak to each other, so they are really not providing independent results. But anyway, if we wanted to do a statistically correct model, we could do that also in the state space framework. It wouldn't change much our estimate. So we're approximating with Gaussianity something that should be closer to a binomial distribution, which for large n is anyway, it's kind of Gaussian looking. Okay. So let's go further with presenting two more important components for the unobserved component model, so that we have also mainly something to deal with seasonality or seasonalities when there's more than one, but also possibly with so-called stochastic cycles that, for example, in economics are very common because of the business cycle. But something can be very useful also in natural data. For example, there is this famous time series, which is also in R, which is called sunspot, and you clearly see a cycle in the data. That's not economic, it's natural, it's just the number of sunspots counted every year, or something. There's also the monthly version of it. So it's about solar activity, but it looks like solar activity has some kind of cycle, cyclical behavior, and the cycle is about 11 years. So of course, in economics is important, but also outside of economics, it can be very relevant. We'll start, of course, with the cycle, because the cycle, the stochastic cycle, will be useful also to build one seasonal version of the deterministic seasonality based on sinusoids. Okay, so let's start with the cycle. Let's go back to last lesson. I told you how are the unobserved components built. How are they made stochastic? So the idea is we start from a deterministic function. We rewrite that function in an incremental way, so like a difference equation. Or incremental way, it's more familiar, it's less scary. If I say in differential form, it sounds too scary. So let's say in incremental form, and then we add some noises so that that component from deterministic becomes stochastic. So what would be the function you use for a cycle? I mean, I don't know so many functions that go up and down that way. So sine and cosine, of course, they're the best function to produce something that goes up and down in a regular way, okay? So we start from the cosine of sine. Sine and cosine are actually the same object. Sine is just the cosine shifted by some quantity, okay? So it's really the sinusoids, okay, which we're interested in. So one way to derive the sinusoids, if you remember going back to your trigonometric courses, you probably saw that the sinusoids were presented like in a Cartesian plot. You take the unit circle, and of course any points on the unit circle, if you project it on the x-axis, you get the cosine, and if you project it on the y-axis, you get the sine. Okay? So this is our starting point. So we have to write a sinusoid in incremental form. Actually, to write a sine in incremental form, we would need two legs of the variables. Or we can like play a trick and use just one leg, but two variables. So does anybody of you know this matrix, which I will call R of lambda? Any familiarity with this matrix? It's got a name. Nobody did linear algebra or matrix algebra. This should be very popular. It's a rotation matrix. It takes one point in 2 dimensions and it rotates it by an angle of lambda. Okay, so suppose that, let's call this point, we will be calling this psi, we can call it psi 0 and psi star 0. I didn't invent these names. They're the names used in the literature. So this is a point in 2 dimensions. Actually, it doesn't have to be on the unit circle. It can be on any circle. Okay. If I apply, so this is a vector. We can call it. If I transpose it, I can call it just a psi vector. If I apply this rotation matrix to that vector, I get a new vector, which we can call psi 1. which is on the same circle, and we just moved clockwise, so this direction, by an angle lambda. Okay, so the new point is called 0. Okay, and of course we can go on and on. We can apply it again and again and again. And what happens is that you see that if you project, so what's the first element of this two-dimensional vector? It's just the projection on the x-axis, okay? And of course, the psi star is the projection on the y-axis. So actually, I've just found a way to write in incremental form a sinusoid, any sinusoid, on any circle. It doesn't have to be a sinusoid of radius 1. So moving between -1 and 1, it can be on any circle. So the amplitude is already free. And also the angle by which it jumps on every time, it depends just on lambda, on the value of lambda. So it's just like a sinusoid of any amplitude observed at discrete time points, okay? So if I let this move again by lambda, and then again by lambda, and so on. So these points are always displaced by lambda, okay? And so, and of course, I'm moving around, but of course, the first element is just the value on the x-axis. So this is just like observing the cosine, for example, on a grid of time points. We can try that with R. It's pretty simple to see it. Okay. So in general, we can say that the value at times t plus 1, or for t equals to t plus 1, is just equal to R applied to psi at time t. So this is just the incremental form, so finite incremental form of a cosine and a sine. Okay. Of course, I have the cosine in the first place and the sine in the second place, in the second element. Okay. We just need any one of the two. It doesn't really matter. Usually, we take the first one. It's really arbitrary which one of the two we will use. Okay, so we have the incremental form. What about making it stochastic? Well, easy. We have a white noise, a bivariate white noise. And usually we assume the two variances are equal, just so we have, and they're uncorrelated. So in that way, we just have one more parameter. So we just assume that the variance of kappa is a common variance times an identity matrix, okay? So there's just one parameter to estimate in this case. In order for the model to be identified or identifiable, we could we could either have two different variances or a fixed variance for the two elements and some correlation. So we have like 1 degree of freedom less than what we could have, but this is fine. I mean, we don't want the model to be too flexible. It's flexible enough. Okay, so that's an assumption. So going back to our drawings, so we are starting on from a point on this circle. What happens? Well, first of all, I apply R, and this makes this point, I don't know, maybe go to here. So the first movement, this is due to the rotation matrix. But then I add some random noise both on the x-axis and on the y-axis. So maybe simplest way to show this. What's happening? Boh. Volevo solo cambiare colore. Non ci riesco. Well, we can draw like contour of the Gaussian distribution around here. And of course, I can fall on any reasonable number of this like two bivariate Gaussian density distribution, okay? So maybe the next point is going to be, I don't know, here, okay? As you see, the effect of K, of this bivariate white noise, is moving both on a different circle, we changed the circle, and also with a slightly different angle, or instead of lambda, we have a different angle. So lambda will be like an average frequency. So I can produce cycles that are longer, cycles that are shorter, but there is like an average cycle frequency, which is lambda, okay? And in this case, actually, we can show that this process, this bivariate process, actually it's just a VAR, so a vector autoregressive process, is non-stationary. Actually, the two roots, so the two solutions that the characteristic equation has, they're both on the unit circle. What does that mean? Well, it's non-stationary. Is that a problem? It doesn't have to be a problem, but it could be a problem. For example, if you want to use this model for the business cycle, so in economics, or anything related to the economic activity, well, economists tend to think of the business cycle as a stationary component. Why that? Because the business cycle is like a reaction, a mid-term reaction or short mid-term reaction to some shocks. So there is a shock and the economy like fluctuates for a while, but then it forgets that shock. Just to get even more concrete than that. For example, in 1973, there was a big oil shock. I don't know if you did some economics history. There was the first big economic shocks. Price of oil rose, I don't know, double or whatever. Of course, all the economies of the world were shocked by that, and of course that provoked a big downward cycle in the GDP of every countries. And then, of course, the shock was released. So after a while, the oil prices went back to a normal price. And so that was like a short-term shock. If I have a non-stationary system, in some way, it means that that shock is still provoking some kind of oscillation or some kind of movement, up and down movement today, which is really not credible. So it's like our business cycle, if I have a model which is non-stationary for the business cycle, is still shaking because of that 1973 shock, okay? So if we have non-stationarity of the cycle, that's the effect we're observing. And that's not realistic. We observed that shock already in the 80s. So it doesn't make any sense that we have a non-stationary cycle that is still shaking today for something that happens like 52 years ago, okay? So we want a stationary process for that cycle. How do we make it stationary? Well, we just add one more thing, which is simple, is a number which we call ρ. It's called, well, ρ is between 0 and 1. So if it's strictly less than 1, then it's stationary, and it can be zero. Of course, if it becomes zero, then the cycle is not a cycle, it's just a white noise, of course. But anyway, rho stays between 0 and 1. The closer to 1, the longer the persistence of the cycle, or the shock in the cycle. The closer to 0, the more similar to a white noise, so the less evident is the cycle. This is called damping factor. And in some way, you can kind of interpret it as AR1 coefficient. Okay, if you remember the AR1 coefficient, if it's 1, we have non-stationarity. It could be also -1 here. It could be also -1. Where we just fix it between 0 and 1 because of identifiability. So if it's closer to 1, it's very persistent, as in the AR1 case, and if it's close to 0, it's very close to be white noise. Okay, so generally we observe cycles with rho which is very close to 1 because they're persistent. They last. At least if we have like monthly data, cycles tend to last years, so many tens of observations. Okay. And so what we added is that if this is our plot, too bad that I cannot manage the color. I don't know why. Ah, here. So if I make like raw red, so the effect of raw is moving in this direction. And in that case, of course, the Gaussian distribution will be around that new point. So it would be just like this green one. Okay. So I have first the rotation, then I have like a compression toward the center, like a attraction toward 0, and then the random effect. This like attraction toward the 0 is the factor that makes the cycle stationary. So it will tend to move around a fixed circle. Okay. While if I put a rho equal to 1, then the circle, I can kind of reach any circle size. Okay. But if I have this rho that attracts towards 0, then I cannot reach any circle size. I'm kind of attracted toward a fixed circle. Okay. And so that's the best way I can explain how this object was born. Okay. That's my reverse engineering. I'm not sure if it was born this way. I rationalize this as this object here. Okay. This is you don't see it. It's actually an ARMA 2.1 process, but you don't see it. Okay. Maybe we can just build like an R function to simulate from this, just to get acquainted as we did for the last time for the local linear trend. So we get acquainted a little bit with how they look like. And then we go back here because, of course, we can use the sinusoids, actually the non-stationary sinusoids, also to build the seasonal, one of the seasonal components. Actually, we could have different forms of seasonal components. But of course, the one based on sinusoids, if you want stochastic sinusoids, so if you want the seasonal components to evolve over time, then we need this object here. Okay. So let's go to R and play around with, let's just build a function that takes maybe the initial values of, so psi 0 or psi 1, takes rho, takes lambda, and then just generate the time series, well, a bivariate time series of psi and psi star. So we can call it, I don't know, R cycle. R just because when there's something random going on in R, it's called R. Like R norm, R t square, whatever. So it's a function. For maybe the first thing to give is the number of observations of time series observation we want, time points. Then we have to pass rho, we have to pass lambda, and we have to pass well, sigma k, or let's say standard deviation of kappa. Actually, it's kappa, like it is the Greek letter. And finally, we also need initial values. So psi 1, for example, or psi 0, psi 1. It's of course, it's a vector with two objects, okay? So I will not try to make an efficient function. I will try to make a readable function, okay? So we will use a for loop for this thing. First of all, think that usually we want the variable in columns and the time points in the rows. So we kind of have to transpose this object here, because here we are working, of course, with column vectors, but we have to transform those column vectors into row vectors. So we have to it's fine. We just have to transpose everything here, okay? I would start with providing a container for the psi. So it's a matrix. It will be a matrix of n times 2. So n time points 2 time series, which is psi and psi star. And we can generate all at once the k's. It will be also a matrix of n times 2. And then we can loop to create every single, it would be every single row of the matrix. So actually we have like a matrix of size. We can initialize it with zeros, and it's going to be n times 2. If you want also, just for making things more readable, let's give names. So we don't want row names, we just want column names, and we can call it psi and psi star. Okay. And then we can already set the first row to be equal to the psi 1. Okay. So psi 1 are the two starting values, one for psi, one for psi star. Okay. And then we do the same thing with kappa. I just leave A instead of kappa. It's going to be a matrix. We can already put Gaussian numbers here. Now we will fill that up, but we will generate Gaussian numbers. And again, it's n times 2. So we have to generate 2 times n observation, and we want the standard deviation to be Sdk. Okay? So this is going already to be our whole. Actually, for some thing that may appear strange in R, we don't even need to transpose all the computations. One more thing, let's generate also the R matrix, so we can call it MR, because we will be using that. It's just a fixed matrix, which can just generate it once and then use it for every time point. And it's a matrix, of course, 2 by 2 matrix, and it has the cos of lambda. Then think you have to go down, not right, but down. This is how matrices are filled up in R. So it's minus the sine of lambda. And then we have sine of lambda. And then we have cos of lambda. Okay. So where? Oops, something is missing here. Over here. No. So cos of lambda minus sine, and cos. Okay. And then we can start the loop. So it would be from 2 to n. And as I told you, for some funny way, R works, we can also avoid the transpose. I told you we have to transpose everything, but actually it works anyway, so we don't have to transpose it actually. So this will be the vector at time t, which is equal to rho. Actually, we could, it's stupid to compute rho times r every time. So let's just add here times rho, okay? Oops, rho. Okay, so this is r multiplied by rho now, okay? It's stupid to do a multiplication so many times when we can do it just once, okay? So here we have mr times m psi at times t minus 1 plus, and we can add k at again, oh sorry, here's t minus 1. Okay, and we return m psi. Is it clear what's happening here? Well, it's just the transposition of what we wrote on paper in a function. But if there's something that you don't understand, just ask. I think clear. Okay. So this should work. Let's try it. Okay, it's not working because in is missing here. Okay. So let's try, I don't know, we can generate like 200 observations. As I told you, well, let's start with a non-stationary cycle. So I put rho equal to lambda. Maybe it's more readable if we give all the names to the parameters. Okay, lambda. Lambda, if you remember, lambda is the frequency. Actually, we call frequency also including 2 pi. So for example, if we want the cycle to be on the average 20 observations long, so the period of the cycle is 20 observation, how do we get the frequency? It's 2 pi divided by 20. So if you want the frequency for the period, you take 2 pi and divide it by the period. If you want the period from the frequency, the period is equal to 2 pi divided by the frequency, okay? Just because in our definition of frequency, we include the 2 pi's. The real definition of frequency that engineers tend to use is net of 2 pi, okay? It's a matter of naming, okay? So lambda, for example, let's create an average cycle of 20. So it's 2 pi divided by 20. This will produce a cycle that on the average lasts 20 time periods or time points. Okay, what about initial value? Arbitrary, I don't know, 1, 2. It's psi 1, actually. Okay, for a non-stationary process as this, the initial values can be arbitrary because anyway, the non-stationary process will move on any circle. For a stationary process, we could be very distant for the attractor circle, and then so if we're very distant, we will have there will be some time for adjustment before starting oscillating around a fixed amplitude. We will see that. But this is now, for example, now this is the variance. Sorry, I forgot the variance. So actually the standard deviation. Well, let's just put 1 to standard deviation. Okay, it worked. So we can see this in 2 ways. We could see this, well, as a time series, actually it bivariate time series. And this is the way we want to see it. Okay, anybody of you will have a different plot, of course. We see it's very irregular. Why is it very irregular? Well, maybe just because the variance is not that large. But you see it's evolving over time, okay? And this will be the object. Well, this is the psi, this is psi star. As I told you, we could pick any one of those. Those two are actually orthogonal. So if you compute the correlation between these two is zero by construction. So this object will be the object we will be using, for example, for building seasonalities. Of course, in seasonalities, we need many of them, okay? And we have to combine them, we have to sum them, okay? In my case, the oscillation is getting larger and larger, but it doesn't have to be so. Probably you have different design. Maybe it goes from larger to smaller, or smaller and then back larger. I mean, I'm talking about the amplitude. But you see that the peaks are on the average about 20 observation far away. About it's just the average period or average frequency. Okay. Maybe you can see that very clearly if you build the ACF. So, for example, of the first one, the first column. So you see the peak goes back 20. So the average period you can also see from this. Actually, it's maybe it's a little bit too long for this plot. Maybe I should make it shorter, but it would be also nice to plot this in 2 dimensions. So X is actually the first component, and then we have Y, the second component, and we can make a line. Type. Maybe I should pick just maybe the first few. This would be a chaos. Okay, so I'm starting from close to the center. You see, I keep on moving in the clockwise direction, and in this case, I'm jumping every time on a bigger cycle, but it's just by chance that it happened in my case. Okay, so if I run it again, probably will look different. No, it does the same thing. Anyway, now let's try to simulate instead of stationary cycle. In order to make this stationary, we just need to put I don't know, 0.9. One thing I didn't tell you, if we make the cycle stationary, then there must be a mean and a variance. So a marginal mean and a marginal variance. And there is, of course. So if rho is strictly less than 1, then the mean, go back to black. So if rho is strictly between, well, 0 is included, but 1 is not included, the mean of the cycle is 0. And the variance covariance of the cycle is equal to the variance of k divided by 1 minus rho squared. Does they recall you something? This looks just like the variance of the AR1 process. If you go back to the autoregressive process, the marginal variance, instead of rho, we have psi, of course. But I told you the rho has kind of the same interpretation as in the autoregressive process of order 1. So why am I telling you this? Well, because this give us also in some way the size of the circle about which we're going to oscillate. So let's just try this value. Well, in this case, we're not far away from the. So what changes? Well, it's much more shaky, I would say. It's more realistic. I mean, a business cycle would be more something like this. Okay. And for example, in this case, if I change the initial values a lot, we will see that for a while, the cycle will try to move in the direction of the, you see, I gave numbers that were too large. You see, the cycle has to move slowly back to the amplitude where it should be. Okay, because I told you if the cycle is stationary, then there is like a marginal distribution which is fixed, and which is, of course, is around here. And so there is like an average circle about which we're turning, and we can see it here as well. So we start very far away from the average circle in some way. Then finally, we tend to move around like a fixed circle. Okay? And how do I get the initial values in the right range? Well, I just can look at I can just compute the standard deviation here. For example, here would be 1. Well, the standard deviation would be the square root of 1 divided by 1 minus 0.9 squared. So it's reasonable value are like Gaussian numbers with 0 mean and standard deviation, which is 2.29. Okay, so something very like 10, we have really no probability to observe. Okay, so that's why we start very far away from here. So with this standard deviation, you know, if you take like 3 times the standard deviation, you have almost 100% of the standard normal. Okay. So indeed, we see that actually then we kind of tend to stay between this case -5 and 5, which is about even less than three times this number. Okay. So this gives you the unit of measurement in which you can, for example, generate starting values. Okay. Well, you can play around. Of course, you can play with frequency as well, but it's very clear what the frequency makes. Well, the closer I get to non-stationary, well, this is still stationary. But of course, the raw is much more closer to 1, so every shock is much more persistent, and indeed it takes a lot of time to move from far away from the circle to which the cycle is attractor. The initial values takes a lot of time, but eventually it will be forgot. This is in some way something that is showing what I just told you. If I have a very persistent, actually, if the cycle would be non-stationary, then, and this is, I don't know, well, this is positive shock, but anyway, if this is something like the oil shock of back in the 70s, you see how long this single shock makes the oscillation last. Okay? And this eventually is forgot because the raw is still smaller than 1. If it's equal to 1, well, that initial shock is present in every single observation in the future. Okay. But anyway, it's a good model for both cycle things like business cycle, sunspot, or whatever. But actually, the non-stationary one is very interesting because we can use it for building like stochastic sinusoids for seasonalities. Okay, it's got the same role of the sine and cosine we had. We saw that we could build seasonalities using sine and cosines. Well, we can use stochastic sine and cosines to build stochastic seasonalities. Okay, and that's what we're going to do now. So I present you two types of seasonalities that we can use in an observed component model. Actually, there is more than two, but these two are the more popular. One is based on sinusoids, and one in some way called stochastic dummy. So it's more related to dummy variables, even though it's really a little bit different than building dummy variables. And once we have done this, I would say the main components we need to use UCM to model real-time series we have. Of course, we can think of components for other things like outliers, dynamic outliers, so an outliers that has some effects over time. I don't know. I will show you a project I did for, and actually still working for Unieuro for their marketing mix, where I built like special components for their own problem. But anyway, so the basic components, once we finish this, are built, so we can just do some samples exercises. So recall what a seasonal component is. Well, a deterministic seasonal component is, let's see, a process. Usually we call it, say, a process, discrete time process lambda t, where we know that it's periodic. For period S, and it has to sum to 0 over S subsequent time points. Okay. In some way, we already have a definition of, this is already an incremental form definition of the seasonality. We don't have to turn it into an incremental form. This is already an incremental form. Why is it an incremental form? Well, because I can just write it this way. Gamma t is equal to gamma t minus 1, actually minus gamma t minus 1, minus gamma t minus 2, and so on up to gamma t minus s plus 1. So the definition of seasonality is already in incremental form. So how do we make this stochastic? Well, one simple way is we just add some noise here. Usually we call this noise omega. It's just a white noise with variance sigma square of omega. Okay. So this is the so-called stochastic dummy seasonal component. Okay. Of course, it's not. Let's say while we saw the cycle actually was already in state space compatible form, because we had like psi at t plus 1 as a function of psi t plus some noise. So it's already like a transition equation. This is not in transition equation because it's got more lags, but of course you now know that we can apply the trick, the lag creating trick that we use also for autoregressive process. At the end of the day, this looks like an autoregressive process with known coefficients, -1, -1, -1, okay? And so we can just play that trick and get some delays of the lambda t or gamma t, sorry, using more than one state variable. So if I have to put this in state space form, I can write actually we can use gamma 0 would be the basic component, and then we want to create some delays. How many delays? Well, actually, we need just S-2 delays, because one delay we get just by going from the left-hand side to the right-hand side of the equation. So actually, we just need maybe it's more tricky. Do the counting if I start from 0, just start from. So here it should be S-2. Why S-2? Here is actually S -1 here, okay. But as I told you, one delay I get just from moving from the left to the right-hand side of the equation. So what happened? Well, if you remember what we did with autoregressive processes, in order to create lags of the first variables, we just need like an identity matrix here. Why? Well, this is telling gamma 2 at time t plus 1 is equal to gamma 1 at time t. So this is the first leg of the first variable. And then it goes on this way. Gamma 3 is just at time t plus 1 is just equal to gamma 2 at time t. So this is creating every single moving toward downstairs is creating one more lag of the variable. So I'm creating S minus 1 lags of the first variables. And so the first variable is the seasonality. All the other ones are delays of the seasonalities. So the first line, the first row is just all of -1s, okay? And then here's 0. But as actually we already saw that, because if you just think of this process as an autoregressive process of order S-1, then you just apply what we have seen for the autoregressive process in state space form, okay? So this creates delays. So this is the first leg of this. This is the first leg of this. So the second leg of this. So this is just S-1 legs of the first variable. And this is, okay, the noise, sorry. So this would be just a bad way to write the deterministic seasonality. Well, here we can use R, matrix R, and there's just one single white noise, okay? It's just the same thing we've written there, written in matrix form, or in vector regression about the one form, okay? Because we can allow only one delay here, okay? Good, this is one type of seasonal component. Another type of seasonal component, as I told you, is based on the sinusoids that we just presented. And we need, of course, S divided by 2 integer part seasonal component, sinusoids build the seasonal component. So this is the stochastic dummy, and we have the stochastic. Usually you call it trigonometric seasonal component. And if you go back to what we said, I think it was the first or the second lesson, we said actually if we have like a deterministic gamma is just the sum of, let's say, j that goes from 1 to s divided 2 integer part of some cosines. And some sines at same frequencies, and the frequencies are the so-called seasonal frequencies. Oh, times t, sorry, times t. Okay, this we already said. So this pair here is a sinusoid. Remember, the sinusoid is this times some coefficient plus this times some coefficient. So this object here is a single sinusoid. Okay. And actually, the alpha and beta gives us two information, so the amplitude and also the so-called phase, which is the point from which the sinusoid starts. Okay. But anyway, this object here, we already have transformed into the stochastic form, and we just needed to replace this object here by the stochastic sinusoids. So in our case, so this was the deterministic, we moved to the stochastic one by saying gamma t is equal to the sum from j that was from 1 to s divided by 2 of, let's call them gamma jt, and this is just the first component of a stochastic sinusoid. So the generic gamma j, and here we have gamma j star, is just equal to what we have just presented. Oh, sorry, here's +1. And here we usually use omega for the white noise. And it's a bivariate white noise. So we just substituted the deterministic sinusoid by the stochastic sinusoid. Okay? So this is the stochastic trigonometric seasonal component, which is just the sum of the first of the pair of gammas here. And sorry, I put the rho, but rho is really not there because we just want a non-stationary cycle, because the seasonality is a non-stationary component. Okay, it's very persistent. You know, if July for electricity consumption is the highest of the months, Well, that's persistent. That will be probably forever. Okay. So that's why it's fine to have a non-stationary component for, or non-stationary cycle for that component. Okay. Just notice one thing that actually happened also in the deterministic case. If S is even, okay, if S is even, then let's see how this pair of equation, or this matrix equation becomes. So this would be like jt plus 1 s divided by 2 star. Okay, we have cos of 2 pi. Well, just compute lambda once. So it's 2 pi divided by s multiplied by s divided by 2. Okay, so this is the quickest frequency. Okay, it's lambda s divided by 2. It's even, so we have that number. Okay, of course this simplifies, so we have pi. Okay, so we have cos of pi, sine of pi, minus sine of pi, and cos of pi. And of course, then we have also the noise here. Okay, what's cos of pi? Cos of pi. It's minus 1. So this is minus 1. This is minus 1. What's sine of pi? 0. So what happens? The second component is really irrelevant for the first one. So we don't need this one is really not needed. Okay. Whatever number it gets, then it gets multiplied by 0 here. This one gets multiplied. So it's really irrelevant in determining the value of the first component. Right? And indeed, the quickest frequency is exactly determined as minus 1. So it goes up and down every time. Okay. So this is the quickest frequency in case of an even S. Okay. So at the end of the day, we always have, as was the case for the stochastic dummy, S minus 1 state vector or state variable. And this holds for both for the trigonometric version of the seasonality, but also for the stochastic dummy. If you count them, there does. It should be S minus times 2. Actually, it's minus 1. For example, let's put some numbers. In case of like quarterly data, I need the 3 delays. Yeah, it's actually S minus 1. Sorry about that. S minus 1. Yeah, like for quarterly data, I need 3 delays, right? So three previous. So that would be S minus 1. Sorry, I was wrong about that number. Fix it. So they're always S minus 1. Okay. Whatever model you choose. You will see also if S is even, we have like S divided by 2 cosines. We have S divided by 2 minus 1 sine. Okay. And that makes S minus 1. So if I sum this to this, I get S minus 1. If S is odd, well, the integer part is like S divided by 2 integer part plus S divided by 2 integer part is equal to S minus 1. Because it's rounded toward the smallest integer. Okay? So let's suppose if S is 7, for example, for daily data. So S is a seasonality every 7 days. S divided by 2 is 3.5. 7 is that is 3.5, but I have to take the floor. So it's 3. Okay. And the same happens here. So it's 3, it's 6, which is 7 minus 1. Okay. Because we lose 0.5 here and 0.5 here. So it's always S minus 1 state variables. Okay. Unless, of course, and that's something we will be doing, unless we decide to work only on like a fewer number of frequencies, of lower frequencies, as we usually do when we have to adapt a very long smooth seasonal component. Okay. Good. Let's start with, I mean, we have about 15 minutes. Let's just start with our law of air passengers time series, which is very handy. It's already there, and try to build like an unobserved component model where we have like the local linear trend, and we can try it with a stochastic dummy seasonal component and also with the trigonometric seasonal component. Okay. I didn't tell you explicitly now how to build together the various transition matrices and all the other matrices. I would like give you just a brief intuition. So if we have to, suppose we want to add components to the same model. Components we make the state vector longer. And usually, of course, we take it like the trend, which is made of 2 state variables. And then we take, for example, the seasonality, which is made of S minus 1 state variable. We put all these state vectors one stacked over the other one. How should I stack also the transition or matrices and all the other matrices? Well, the T matrices is just like a diagonal concatenation. For example, this is the T of the local linear trend. This is the T of seasonality or whatever. So the T is made by diagonal concatenation of the single transition matrix. And the same holds for R, even though R is not diagonal. I mean, not sorry, it's not square, but it doesn't really matter. You can still like find it on the diagonal. And what about the Q? Q is also the same. And of course, also A1, of course, we stack everything over. So this would be A1 LLT. A1 cycle, so on. So we stack the state vector are one on the top of the other, and of course the P1 infinite is the same, is also diagonally concatenated. Or C's or whatever. What about zeta? Zeta instead is horizontally concatenated. So we would have like the zeta of the local linear trend, the zeta of the seasonal, even the cycles we could have, whatever. Okay? And H remains H, because H is just some noise we're adding to the signal. So H is just equal to H. It's still just one noise we're adding to the whole system. So H is really not. That's why you see that in class, H is placed in a different place with respect to all the other matrices. Okay, because it's just some noise we add to the signal we're doing. So let's just try to build the first model, the first UCM for a time series. Of course, we have to work. Of course, we have to work on the log because it's still a linear model. We are adding components. We are not multiplying components. So it is an additive model. And so we saw that the air passengers time series is multiplicative. So we have to work on the log. So our, I don't know, y, well, we can call it ly, so the log of y. Well, just call it y. It's too stupid to. Okay. I would also do another thing. Let's as I told you last time, as in a modeling state space form, missing observation is really not a problem. Let's just pretend we don't know the last year, maybe, of the time series. So let's put the last 12 months to NA, so that we have like prediction for free of this missing observations. Okay. So we can like fix. I think there are 144 observations. So from 121. So 2 years, actually 2 years. Let's put the last 2 years to NA, and we will be forecasting them. Okay. And there, can you see last 2 years? Okay, let's define the model, the state space 4. So we can call it model 1. We need CFAS, of course. Sorry. Let's load CFAS. SS model, sorry. So here we have to provide a formula, if you remember. Actually, I always need the tilde to steal the tilde from somewhere. Here I can steal the tilde. No. This is today. Okay, here's the tilde. So here. So our time series is called Y. We don't want any constants in the model. Actually, when we put the trend, so now we were going to put a trend by using SSM trend. If you put a trend, even if you don't write zeros, -1 to eliminate the constant will be automatically eliminated, because otherwise the model is not identified, because there are two objects that try to explain the level of the time series. There's a constant, but also here there's like the intercept away, okay? So if you have a trend, you cannot have like an intercept because the trend already includes the intercept in some way, okay? So even if you write 0 or -1, the system will just exclude the intercept. How do we define the trends using SSM trend? Well, the local linear trend is using this terminology is just a trend of degree 2. If we want the random walk, it's a trend of degree 1. Okay? So the local linear trend will be a trend of degree 2. And Q is actually a list that has to contain the variance. If you remember, the local linear trend has 2 equations, the level equation and the slope equation. Each equation has its own white noise, okay? So we need to give 2 variances, one for the first white noise and one for the second white noise. You have to pass them as a list. And you may ask yourself, why as a list? Is it not simpler just to use a 2-dimensional vector? Well, actually, we could have a multivariate time series. And so we could have many local linear trends, one for the first time series, one for the second time series, one for the third time series. And the white noise of all these trends may be correlated. So actually, I could need to put the matrices inside for the vector of betas in the multivariate models and covariance matrix for the vector of zetas in a multivariate model. That's why it's used a list instead of a vector. So we don't know the values of these variances. Okay, let's just put NA. Well, already last time we used this NA to place unknown things inside the. And all the rest, I think we can ignore. By default, of course, if you look here, okay, there is the degree which we have assigned, there is the Q which we have assigned. All the rest, we can just go with the default. For example, the A1, P1, P1 infinite. This is a pair of non-stationary state variables. As I told you, non-stationary state variables, unless we have better information, are set the mean equal to 0, just an arbitrary value. It could be any value. And the variance is equal to infinite. So these 3 matrices are automatically fixed to, well, 0, 0. This also 0, 0. And then we have a diagonal, an I matrix for the P1 inf, so the identity matrix for the Pi1 inf, because it's just telling to the system, I want an infinite initial variance for the first and the second components, which are just non-stationary. And then we have SSM seasonal. Where is it? Here. And here we have to, first of all, there's the period. So we have to pass the period, which is, this is a monthly time series. So the period is 12. Then there is a variance. Here there's just one variance. And then we have to decide which seasonal type we want. And as you see, it includes either the dummy, stochastic dummy, of course, or the trigonometric, so the stochastic trigonometric. Let's start with a stochastic dummy because it's simpler, because we don't have to write our update function. Actually, it's the default, but let's just use it. All the rest, again, we can just use the default because also this seasonality is a non-stationary component. So we will just have mean 0 for the initial condition and infinite variances, okay? And then we just need to add the observation noise, and we can say also in this case, I don't know the variance. Okay, so this is the state space form. And as I told you, if you look, well, if you look at the, for example, the A1 give you also the state vector in some way, okay? Because it's the mean of the state vector at time t equals to 1. So this is the order of the components. So the level of the slope. So first, the trend. It doesn't really matter if you put in the formula first the seasonality and then the trend, because the trend will be always put by the system at the top. And then the seasonality comes. Actually, if we add a regressor, the regression coefficient will be even before the level. Okay, we will learn that by doing that. So we have the two variables for the trend, and then you see we have the 11 variables for the 12 months seasonality. Okay, this will be the seasonality, and this will be just legs of the seasonality. So the first leg is a leg up to 10 legs. Okay. So if you look at the T matrix, which is very huge now, you see here we have, well, this upper left part, this is the, if you go back to the local linear trend definition, we have 1, 1, 0, 1, and that's it. And then, as I told you, we join all the components by diagonal concatenation, okay? So below and after that will be all zeros, and then here we have the matrix, the transition matrix for the seasonal components. Indeed, you see the minus ones, of course, then it goes on, and the identity matrix that creates all the delays of the seasonality, okay? And goes on here, of course. Here's the diagonal, well, the minus one and the diagonal going on. And the same happens, as I told you, for R. So here we have just 3 white noise in the transition equation. We have what we call the eta. The eta is assigned to the level. Then we have the zeta, which is assigned to the slope. And then we have the so-called omega, we call it white noise omega, which is assigned just to the first state variable of the seasonal component. All the other ones are just identities, so they don't have noise. So they just receive no noise. And so the Q matrix is just a matrix with 3 by 3 variance and covariances. We put them to NA because we don't know them and we want to estimate them. So these are just NAs. What is missing? The zeta, for example, the zeta matrix. Well, the zeta matrix, you see, is just like a selection matrix in this model. It just selects the level. It put the slope to 0 because the slope is just useful for building the level. And the same thing, it just takes the first component of the seasonality, because that's the seasonality. All the other ones are just leg of the seasonalities, but then I have to be assigned to the y variable. And finally, we have H, which is just a scalar, which is the observation noise variance. Okay. As I told you, a nice thing about CFAS, this package, is actually we have all the freedom to build our custom state space form, but if we use components that are standard, well, we already have them, so we don't have like we did last time. So last time we built the state space form from scratch using SSM custom, okay? Because it was a particular model customized to the aim of the polar poles problem, okay? But in this case, we use like more standard components, then we don't have to write ourselves the system. The system is written just by using this formula kind of symbols or functions. And actually, we're running out of time. Well, the nice thing about this model is that we can estimate it right away without writing the update function, because all we have to estimate is just on the diagonal of the Q matrix and the H matrix. You remember, I told you there is a default update function that just assume we want to estimate the variances on the diagonal of Q and H that were put to NA. And so we can just finish this example, and then we will go on next time with the same example. We can fit this model by calling fit SSM. The first thing to pass is the model. The second thing to pass is the initial values for the parameters we want to estimate. Remember, first are the diagonal of the Q and then diagonal of the H. So we have just 4 parameters, and they're all variances. And remember, the default update function actually wants the log of the variances, because so the exponential is always positive. Let's just, it will be very small numbers because it's all in logs. So I just put not reasoned initial values, could be like the log of, oh, I don't know, 0.1, 0.001. So the variance of the level of the slope and of the seasonality, which is also usually small because it moves very slowly in time. And then a little bit larger, the observation noise variance. It's only log, that's why are so small numbers. I'm just putting some numbers, it's not really. And I don't need the update function, because in this case we can use the default update function. Let's see if it's working. It worked. Always check the convergence here. 0 means it converged. Have to go, so we will pass the common field transmuter in the next lesson. Do you have a lesson? Avete una lezione adesso? Well, we finish the example next time, okay? Anyway, we will start in doing many examples of this type with more and more complex time series, like daily time series and so on. But now we have all we need to apply the UCM world. Questions?